In this video, we are going to discuss the joint expectation of joint distribution. So we are considering a bivariate distribution. So we will talk about bivariate distributions. If we have two random variables x and y with joint distribution f of xy, then mean or expected value of the random variable g of xy. Here we are considering a function of two random variables x and y, which we are denoting by g of xy. So this is the function of two random variables x and y, their joint function. So their joint expectation will be denoted by mu of g of xy. G of xy is the required function for which we have to compute expectation. So expected value of g of xy is equals to procedure is similar function into probability, and we sum over the entire range. Here we have two variables, so we will use joint density and two summations, one for x and one for y. So if we have more than two variables, then we will multiply by joint distribution and a summation for every variable that is in the distribution. So this is the formula we can use to calculate the joint expectation of random variable x, y from the joint distribution. This function g of xy could be anything. It could be x minus y, x over y. There are plenty of options available. Whatever the function is, we can calculate expectation using this formula. Furthermore, we can also compute the expected value of x, expectation of a single random variable from the joint distribution. How can we do that? We have to compute expected value of x. So our function g of xy is equals to x. So simply replace g of x by x in this formula. So we get summation xy x into f of x y. Here we can observe that we can reduce this formula to this. So if we are using bivariate distribution itself, we use double summation x, one for x and one for y. But if we are using marginal distribution, we can use that simplified formula. Okay, these formulas are equal. So, we can observe that why? Because summation y f of xy equals g of x. So this formula is the simplified version of this. Similarly, we can calculate expected value of y. What we would do? We would simply replace g of x by y, and when we apply the summations, we get this simplified version. So we can use the joint density and the marginal densities, whatever is convenient or available to us. We have discussed these rules of expectation for the joint densities of joint distributions of x and y. Now we can also calculate the variances for the joint densities from the joint density. If we want to compute the variance of x from the joint density, what we will do? We will simply write double summation x, y. So for variance, what we had to do? We had to x subtract mean from x square and f of xy. So this is our general formula. We replace g of xy by x minus mu square. So then we get the variance of x. So we can simplify it as, so if we are using marginal density, we can write it as x minus mu square into g of x. So it's simple, as we have practiced before. So if we want to calculate variance of y, it would be again like summation x, summation y. Now we will use mu y minus mu of y. We will use subscripts to differentiate two means. This is the mean of x and this is the mean of y. So we can write it simply. F of y is summation y minus mu of y square into h of y. So from joint density, we can use this formula, and for marginal, we can use this formula. Furthermore, when we have two variables, we have another quantity that we can compute. It's the covariance of x and y. Covariance tells us how the two variables are related and how their variation is connected. how does these two variables vary together? So we can compute covariance of x and y. So what would be the covariance? Since we have a joint density, so we have two solution, one for x, one for y. Now we want to compute the covariance of x and y. So we will replace g of xy by x minus mu of x, y minus mu of y. The x part and the y part multiplied by their joint density. So this is the covariance of x and y. We also know that we have shortcut formulas for variances. So we have a shortcut formula for covariance. What is the shortcut of variances? It's usually expected value of x square minus expected value of x whole square. And for y we can write expected value of y square minus expected value of y whole square. Similarly, we can write a shortcut formula for covariance. What that formula is, it's expected value of xy minus expected value of x into expected value of y. So we can use any of these two formulas to calculate the covariance. So what is the expected value of x? We know what is expected value of x and expected value of y. We have discussed earlier. Now what is expected value of xy? We simply replace g of xy by x into y. So we get summation 1 for x, 1 for y. G of xy, now we have xy into their joint density. We will solve this and get the expectation xy. And we can then use them to calculate covariance and marginal densities to calculate variances. Now let's practice these expectations over a question. Now let's practice our joint expectations with this joint distribution. The first I want to discuss is the joint expectation of any variable g of xy. So I am going to use the function 2x minus 3y to calculate the expectation. So our function is 2x minus 3y. Let's compute the expectation. What is the formula of expected value of gx? Y is equal to double summation xy, and we have g of xy f of xy. So let's substitute our values. We want to compute expected value of 2x minus 3y. So we may write summation over x, summation over y. What is our function? Our function is 2x minus 3y and f of xy. So what I'm going to do is I'm going to substitute all pairs of x and y one by one, and then we will compute our expectation. So first is when x is 2 and y is 1. We have to compute this for each and every pair and then add them. So first is when x is 2. So I have 2 into 2 minus 3 into 1 when x is 2 and y is 1. So probability here is 0.10. Summation, we have a summation, so we write plus. Then when x is 2 and y is 3 and probability is 0.20, plus when x is 2 and y is 5 and the probability is 0.10. So next, when x is 4 and y is 1, similarly, and probability is 0.15. We can write all the pairs in a similar fashion. Writing all the pairs and then solving this, we get the expectation minus 2.6. Similarly, we can find expected value of xy. So we'll write summation xy into f of xy. So we will compute this for all the pairs like we have done before. It's 2 into 1, 0.10, and we will write all the pairs and then we will compute this. So we have substituted all the values, considered all the pairs, and multiplication and addition gives us the answer 18.7. So we get expected value of xy equals to 18.7. Now we will compute expected value of x, expected value of y, and then we are going to practice covariance and variances. So here we have computed expected value of x, expected value of y, expected value of x square, and expected value of y square. We got expected value of x 3.2, expected value of y 3, expected value of x square 11.2, and expected value of y square is 11. Now we can compute covariances and variances. For covariance of x and y, we can write expected value of x y minus expected value of x into expected value of y. So substituting the values, we get expected value of xy is 18.7 minus expected value of x is 3.2, expected value of y is 3. So we get 18.7 minus 3.2 multiplied by 3, it's 9.1. And the variance of x is equals to expected value of x square minus expected value of x whole square. So here we have expected value of x square 11.2 minus expected value of x is 3.2 square. So 11.2 minus 3.2 square is 0.96. Similarly, variance of y is equals to expected value of y square minus expected value of y whole square. So it's 11 minus 3 square. 11 minus 3 square is 2. So this is the covariance, covariance and variances of x and y. So this is how we compute expectations from joint densities. I would like to make a correction. I have computed expected value of xy wrong. There was mistake in computation. Expected value of xy is 9.6. So the covariance will be 9.6 minus 3.2 into 3, and the covariance turned out to be 0. If you remember, when we discussed statistical independence, we took similar density and we observed that the x and y are independent. We can observe this trend here since covariance of x and y is 0. So it states that x and y are not related. So we can say that if x and y are independent, covariance of xy is 0. Vice versa, if covariance of xy is 0, we can say that the variables x and y are independent. So this is another way to check independence. There's one more condition that can be used to check if the two variables are independent. It's if two variables x and y are independent. If x and y are independent, then expected value of xy is equals to expected value of x into expected value of y. So we can check it here. We have expected value of xy is 9.6. Expected value of x is 3, and expected value of 3.2, and expected value of y is 3. So if we multiply 3.2 and 3, we get 9.6. So this is another way to check statistical independence. So we have discussed three methods. Number 1, for statistical independence, first condition was f of x y should be equals to g of x into h of y for all x y pairs. Second condition we observed is covariance of x and y is equals to 0, and the third thing is expected value of x y is equals to expected value of x into expected value of y. So we can use any of these three conditions to check the independence of two variables x and y. So girls, this was expectations that we can compute from the joint distribution. We can further compute the coefficient of correlation if we want to. What is the coefficient of correlation? It's rho x y, and it's equals to covariance of xy divided by standard deviation of x multiplied by standard deviation of y. So we can compute coefficient of correlation as well. We have computed covariance, we have computed variances. We can substitute in this and we'll simply get the coefficient of correlation. So these are all the expectations and values we can compute from the bivariate distributions.